Now we're going to take a look at some of the chemical properties and periodic trends. Specifically, we're going to look at the differences in chemical properties of elements in the same group. Alkali metals, lithium, sodium, and potassium with water. Those alkali metals with the halogens, chlorine, bromine, and iodine. And then the halogens with halide ions. So this last one, we're talking about a single replacement reaction. Hopefully you could have guessed that. Green was not a good color for me to choose. Lastly, we're going to end, and there's not a whole lot to say about it, but the reactions for sodium oxide with water, magnesium oxide with water, phosphoric. Oh, no, geez, naming rules. It's a covalent compound, so tetraphosphorus decaoxide and sulfur trioxide. Wow, I don't know why I couldn't think of that. I'll leave that in. Maybe you guys will chuckle. Sometimes I have a senior moment. This is when you should tell me that I look young. Thank you. All right, moving along. Sorry. Periodic trends. Alkali metals are going to react with water to produce metal hydroxides, hydrogen, and heat. Okay. And really, remember when we were doing single replacements and we were talking about thinking of water as being a hydrogen bonded to a hydroxide? Lithium going to be kicking out the positive part to make the lithium hydroxide. It will liberate hydrogen and heat. This is a base, so this will form a basic solution because that is soluble in water. So if we put phenolphthalein in there, it should turn pink. Same with sodium. Sodium metal with water, sodium hydroxide, hydrogen, and heat. You can sometimes release enough heat that you will ignite the hydrogen. Going down further in the periodic table, we have potassium with water making potassium hydroxide, hydrogen, and a lot of heat, likely to ignite the hydrogen. And the screencast would not be complete without showing a little video.
Lithium, sodium, potassium, rubidium, cesium, and francium. They're all soft metals which can be cut with a knife. In air, the elements quickly become coated with compounds that form on the metal's surface. Here, for example, is lithium. When we slice it, you can see the metallic luster, but the black coating quickly reappears. Sodium is kept under oil to prevent reaction with air. Again, when we cut it, the metal surface can be seen. But this time, corrosion occurs even more quickly. With the next alkali metal, potassium, the corrosion in air is so quick that it's hard to see the metallic luster at all. As we go down the group, the elements seem to react more quickly with air. Now let's see another reaction of the alkali metals, the reaction with water. We'll start with lithium. The metal floats on the water and reacts with it, giving off hydrogen gas. Now for sodium. The same sort of thing happens, although the reaction is a bit more vigorous. All the alkali metals react with water in the same way. Let's see an equation for the reaction. Hydrogen gas is produced, and the metal dissolves to give an aqueous cation with a single positive charge. Now for potassium. This time you'll see a flame. The heat given out by the reaction is produced so quickly that the hydrogen gas catches fire. It burns with a line of flame. The rubidium. This time, we put a safety screen between us and the reaction. You can see that things gradually become more terrifying as we go down the group. Let's try cesium, our fifth alkali metal.
Well, that was pretty neat. Okay. So, continuing, you are required to know these equations. Hopefully they make sense with the types of reactions that we did in 10th grade. All right, so those were the three. What do they do when I have a metal and a non-metal? Well, hopefully you can guess. My metal and my non-metal making a ionic compound and releasing some heat. Okay. When I do react lithium and chlorine gas, sometimes you need to put in some energy to get the reaction going, and then it will be exothermic, releasing heat. As I go down with the more reactive sodium with chlorine, a lot of heat is released. And then potassium, very vigorous, making the potassium chloride. I do have another video. Let's see if I can, of sodium and chlorine.
Sodium metal is heated until it melts and just begins to burn. Then it is immersed into the yellow-green chlorine gas. The sodium begins to burn in chlorine with an intense yellow flame. It produces a white smoke of sodium chloride. We are observing the exothermic reaction of sodium metal with chlorine gas, producing the white solid sodium chloride. Afterwards, the glass spoon contains only white solid sodium chloride.
I thought that was kind of cool. Okay. Okay, so those were the three. And then what happens when I react halogens with halide ions, displacement reactions? Now I want to point out something. In this reaction, you can see I have potassium, bromine, chlorine, making potassium chloride, and bromine, and releasing a red color. This, hopefully, you may have recognized this as a net ionic equation. This is aqueous in solution, making potassium ions and bromide ions. This is potassium ions and chloride ions. Potassium is what we call a spectator ion. Spectators can get canceled, and we have this overall equation. It is a replacement or a displacement reaction. The more active or reactive halogen replaces the ions of the less reactive halogen. How do we know which is more reactive? Think about the trends. Think about if something has an ability to attract electrons more, might that be more reactive? And what element in the halogens is likely to be able to attract electrons more? Hopefully you're saying at the top. So those would be a single displacement reaction with a halogen replacing a halide ion. The more reactive halogen will replace the ion. All right. Here we need to really just know the properties of the third period oxides. So we're looking at oxides of sodium through to chlorine. Take note of the different ions, of the different oxides that phosphorus, sulfur, and chlorine can make with oxygen. All right. We go from solid ionic compounds to these more covalent compounds, okay, being a solid, a liquid, and a gas. As they get less I was going to say massive, but I'm not sure if that's just London dispersion. There's got to be some dipole-dipole going on with these as well. Okay, melting point, wow, minus 92 degrees Celsius to a high of 2800 degrees Celsius. Ionic, silicon dioxide being a covalent network, meaning it is a lattice structure of covalent bonds, and then covalent compounds when I get to phosphorus. Electrical conductivity, hopefully you realize that when they say good, they are talking about when it's melted or dissolved, not in its solid form. Okay. My covalent network, very poor electric conductivity, and then my covalent compounds, not at all. If I put these with water, my sodium oxide is going to make sodium hydroxide, magnesium hydroxide. The aluminum oxide is amphoteric, and we'll take a closer look at the aluminum oxide and its structure. Silicon dioxide is amphoteric, and then when we get to the nonmetal oxides, those are acidic. Here's where you need to remember the different ions. I have phosphoric acid and phosphoric and phosphorus acid, okay, from these two compounds. Okay, and we can do those equations in class, we probably will. Sulfur trioxide is going to make sulfuric acid. Sulfur dioxide is going to make sulfurous acid. And similarly with the chloride oxides. And we will take a closer look at those in class. Hopefully come up with a way of remembering this entire table. But we will take a closer look at some things in class.